Today we're going to talk about Chapter 8 Equilibrium, Part 3 Industrial Processes, Acid and Bases, Theory and Questions. Let us start. Okay. Now, so for today, what we are going to do is first we're going to talk about Haber process and contact process. Okay. Then we're going to understand about Bronsted-Lowry theory of acids and bases and know the difference between strong and weak acids and strong and weak bases. Okay, so that's what we're going to do today. Okay. Now, for Haber process, this is a well-known industrial process to form ammonia. Okay, a few things to note about this. Why is this inside the chapter? Because of this equilibrium error right here. So this is a large-scale industrial process involving an equilibrium reaction, a very famous one known as Haber process, named after Fritz Haber. Okay. Other things to take note of is that it is, because of the negative sign, exothermic. Okay, a few other things to note of. Okay, here is 4 moles of gas, and here is 2 moles of gas. Okay, so in this process, first please take note, we use iron. Okay, so this is a catalyst that is meant to increase the rate of the reaction forward and backward, but does not interfere with the reaction. Okay, no, sorry, let me reiterate, does not interfere with the reaction, does not interfere with the yield of the ammonia, because it cannot affect the equilibrium. It is meant just to increase the rate of reaction. Now, next thing we note is that they use a high temperature. As we all know, what did I teach you? What did I say last time? First, because it is exothermic, okay, plus heat. Okay, next, you use a high temperature. What happens? Heat increases, then equilibrium shift to the left. What happens to your ammonia? Your ammonia unfortunately decreases. So why do they use a high temperature when they want to get out more ammonia? When increasing the temperature results in lower amounts of ammonia. And there is only one reason. Okay, 450 degrees, although it decreases the amount of ammonia, is to increase the rate of reaction. Unfortunately, if the reaction is too slow, even if you form a lot of ammonia, at the end it will take a long time. Chemical engineers have calculated they would rather get small yield of ammonia in faster time. Over days, they will eventually get a lot of ammonia. So that's why they prefer to increase the temperature. Okay. Next, high pressure. Now, if there is high pressure, okay, let me, okay, because this is 4 moles of gas, this is 2 moles of gas. Okay, what happens is that the pressure is high. In order to shift the equilibrium to the right, because there are less gas molecules on the right. So if you realized, reactants is 4 moles of gas, products is 2 moles of gas. Because there are less gas molecules on the right, when you increase the pressure, Le Chatelier's principle, in order to reduce the increased pressure, shift to the right to form less gas molecules. Okay, and that's why they did it in high pressure. Okay. Next, we're going to talk about contact process. For contact process, okay, the first one is that sulfur liquid. How do you get sulfur liquid? First, you heat up solid sulfur until it melts, react with oxygen, and then they will form SO2. Okay. Next, the SO2 is gonna react with oxygen in an, now this is the key one, that's why you study this in this chapter, equilibrium reaction to form 2SO3. So let us study this equilibrium a bit deeper. Okay. Now, if you were to take note, this is also another exothermic reaction. And therefore, heat is on your on your right. Now, so the catalyst is vanadium 5 oxide, V2O5. The temperature is 450. Okay. Now you must be thinking, if temperature increases, equilibrium shifts to the left. Okay, causing the amount of products to reduce, and that is correct. But again, the reason is similar to Haber process. In order to increase the rate of reaction so that you get your sulfur trioxide faster. Okay. Now, then you may say, sir, this is similar to previously because here got 3 moles of gas, whereas here got 2 moles of gas. You must be thinking, so why didn't they increase the pressure? The biggest reason why they did not increase the pressure is because of this. The pressure remains the same in order to save cost. The higher your pressure, I want you to think of your wall of the container. You cannot put inside a thin container like this, you must put inside a thick container like this. Okay? So therefore, in order to save the cost, they realize if they put it at 1 atmospheric pressure, Yes, they will get a little bit less of SO3, but the cost of making the container is a lot cheaper. Okay, and the reason there is no need to force the reaction to move to the right, because this reaction, the equilibrium actually lies more to the right. If when they reach equilibrium, in this particular equilibrium there are more products than reactants. In the Haber process for ammonia, the equilibrium actually lies more to the left, which means when they reach equilibrium there is actually more reactants. So because of this, they have calculated out, even with 1 atmospheric pressure, they will still get a lot of the products. So in the overall, they prefer to save cost. Okay, next, please take note that, okay, sulfur trioxide does not straight away react with water to give you your sulfuric acid. You first react with pure sulfuric acid to get what we call this oleum. Then only the oleum reacts with water to give you pure sulfuric acid. The reason behind it is addition of water to SO3 is an exothermic reaction. Because of that, if you add water directly to sulfur trioxide, you are going to release a lot of heat, which you are not going to get sulfuric acid liquid. You're going to get sulfuric acid gaseous. In an industrial process where you have 100 ton or you're forming that much, you don't want to have gaseous sulfuric acid. So they rather do this step, okay, less exothermic, but you still get sulfuric acid in liquid form. All these two, contact process and Haber process, are what we call industrial process, run on a large scale, okay, in order to form a lot of products. Okay, so therefore they have optimized it where they realize they can get the most products in the fastest way with the cheapest cost. Okay, and I hope you can see what you have learned previously, Haber process and contact process. You are learning it right here. Oh, sorry about that. Let me move this. I hope you guys can see it. Sorry. Yeah. Okay. Okay. So addition of H2O to SO3 is an exothermic reaction. Okay. Now, now we talk about something different. We talk about strong acids. Okay. Now, strong acids are acids which dissociate almost completely in water to form hydrogen ions. Hydrochloric acid, sulfuric acid, nitric acid. Okay. Key one, dissociate almost completely. Weak acids are acids which only partially dissociates in water to form hydrogen ions. The key thing to note here, because they say partially dissociate, which means that when it form the hydrogen ion and dissociate and form sorry okay okay now for this, because partial dissociation, therefore take note, it is actually an equilibrium reaction where the hydrogen ion and the ethanoic anion can combine together to form ethanoic acid. That is what we mean by partial dissociation, and that is why it is in this chapter 8, equilibrium reactions. So the dissociation of weak acids is actually an equilibrium reaction. Okay. So some other weak acid like hydrocyanic acid, hydrogen sulfide. Okay, so like I said, take note, fully dissociated, partially dissociated. Because there are a lot of hydrogen ion, therefore the pH is low. Because there is some hydrogen ion, therefore the pH is higher for weak acid. Strong bases are bases which dissociate almost completely in water to form hydroxide ions. Sodium hydroxide, calcium hydroxide. Weak bases are, on the other hand, bases which only partially dissociated in water to form hydroxide ions. For example, ammonia methylamine cyanide ion. So therefore, like ammonia, if you put it in water, you are going to form ammonium hydroxide. Again, take a key note, it is actually an equilibrium process, whereas strong base is a irreversible reaction. Because sodium hydroxide completely dissociate, there are a lot of hydroxide ion, high pH. Because ammonia is a weak base and only partially partially dissociated this forms some hydroxide ions. Take note that it only forms some, therefore lower pH. Okay. And that's the difference between strong acids, strong bases, strong acids, weak bases, strong acids, weak acids, strong bases, weak bases. Okay. Okay, now we are going to learn something new.
Okay, now let us talk about, sorry, not about this one. Bronsted-Lowry theory of acids and bases. Now, previously, you have learned for acid, okay? Acid is a substance that dissociates, okay, to form hydrogen ion in water. Okay. Base is a substance that dissociates to form um, hydroxide ion in water. Okay. Now, unfortunately, a problem arises. Okay. What is the problem? Now, for example, if you have, sorry, let me use this. You have ammonia reacting with HCl to give you NH4Cl, ammonium chloride. By all accounts, we acknowledge that HCl is an acid. But ammonia, okay, is a base. We also acknowledge about it. But when they react, first, they do not form water. Second, there is no hydroxide in here. So do we still call this acid-base reaction? Okay, because you look closely and need no O at all, no hydroxide, and yet ammonia react with HCl to form ammonium chloride. The question lies right now, what do we call this? Do we still call this acid-base reaction? No form water, there is no hydroxide in there. Okay, so at the end of the day, they decide to expand the definition of acid. Okay, so they decide to focus solely on the hydrogen ion, or what we call proton. Okay, and they say this: we ignore hydroxide. Bronsted-Lowry theory of acid and bases is like this: any Bronsted-Lowry acid is a proton donor. Okay, any Bronsted-Lowry base is a proton acceptor. Okay, so can we classify this as acid-base reaction? We can. Why? Now, ammonium chloride is nothing more than NH4 plus and Cl minus. Okay, so we say that because hold on. Okay, because ammonia accept hydrogen ion or proton to form NH4 plus, it is a Bronsted-Lowry base. Because HCl forms Cl minus by donating H plus, it is a Bronsted-Lowry acid. So despite the absence of water, we still call this an acid-base reaction according to Bronsted-Lowry theory. Okay? So this is a new definition that you need to know. We ignore hydroxide. In any reaction, as long as it donates a proton, it is an acid. As long as it accepts a proton, it is a base. We focus exclusively on proton donation or acceptance, hydrogen ion. Now, so how did this compare last time what you studied? Sorry. Previously, okay, what you study is what we call Arrhenius, okay, theory of acid and base. We focus on what we learned here. dissociate to form hydrogen ion, dissociate to form hydroxide ion. Bronsted-Lowry is the same idea. It's just that now Arrhenius theory is the subset. Expand the definition. Okay, so right now, right here, this is Bronsted-Lowry theory. So you guys can see that the previous definition you learned is expanded. So all Arrhenius theory, all Arrhenius acids are Bronsted-Lowry acids. All Arrhenius bases is Bronsted-Lowry bases. But not all Bronsted-Lowry acids are Arrhenius theory. Not all Bronsted-Lowry bases are Arrhenius bases. Okay, because we just now expanded the definition. Okay, now, so before that, okay, sorry. So because of that, so how does this have to do with equilibrium? Okay, now we look at this, we just focus on the forward one first. You agree me, right? Because HCl forms Cl minus, it is an acid. Because H2O accept the proton, it is a Bronsted-Lowry base. Okay, what has to do with equilibrium? Okay, we acknowledge these two, right? Acid and base. Don't forget, this is an equilibrium reaction. Okay, if it can go forward, it can go backward. So now let's focus on the backward part. Okay, because H3O plus become H2O, it is what we call an acid because it donates the proton to form H2O. Because Cl minus accept the proton to form HCl, it is the base. Okay. Okay. So now, what does the conjugate means? At the end of the day, when HCl donate proton from Cl minus, when Cl minus go backwards that time, it form HCl. Because of that, we say that these two is linked. So Cl minus is the conjugate base of HCl. Linked. HCl donate proton, Cl minus. Cl minus accept proton, HCl. Because H3O plus donate proton from H2O. H2O accept proton from H3O plus. We call this the conjugate base. A conjugate acid. So what does conjugate means? Conjugate means linked. Okay. HCl, Cl minus is linked when HCl donates proton from Cl minus. So we call it the conjugate base. When H2O as a base accept proton, H3O plus, we call it the conjugate acid. The word conjugate means linked. The reason why it is acid because in an equilibrium it can go backward. Okay, okay. Another way to say it, okay. this appears in the learning outcome, okay? But I've never seen it appear in the past year paper except for one time only, once or twice, okay? Most of the time they will say acid conjugate base, base conjugate acid. Never, rarely they say acid one, base one, which is just another way of saying, because HCl form no, donate proton form Cl minus acid. Cl minus accept proton base. But why is it one? That one to show that this two is linked. Okay. H2O accept proton form H3O plus base. H3O plus donate proton to form H2O acid. Why got the word two there? Very simple. They are linked. Okay. Okay. That is what I mean by acid one, base one, acid two, base two. Okay. But please remember, the more important thing to understand is acid conjugate base, base conjugate acid. Identify the conjugate bases of the following acid. Since we referred to all of this as acid, so all you need to do for all of them is all of them donate H plus. HBr, Br minus, HNO3, NO3 minus, H2SO4, HSO4 minus, HSO4 minus, SO4 2 minus. This is what happens when all the acids donate H plus proton. Okay. Identify the conjugate acids of the following bases. Please pause this video, try and do this by yourself. Okay. Okay. Now, the answer, because they are bases, accept proton H plus, F minus HF, HS minus H2S, CO3 2 minus HCO3 minus, HSO4 minus H2SO4. Identify the Bronsted-Lowry acids and bases. Please pause the video if you want to do it by yourself. And the answer is, again, focus on the front part. Okay, which is somewhere around here. HCl, Cl minus acid, accept proton base. H2O, donate proton form OH minus acid base. HCO3 minus accept proton H2CO3. Donate proton forming CH3CO minus. Accept proton to form C6H5OH base. Accept donate proton to form HPO42 minus. Accept proton to form H3O plus. What is the shortcut to this? Very simple if you want to identify. Got add H or don't add H. Add H, base. Don't add H, give away H, acid. Okay. Now we have identified the Bronsted-Lowry acid and base. Now please identify the conjugate acid and bases. So we look backward. Okay. Okay. Donate proton, conjugate acid. Accept proton, conjugate base. Donate proton, conjugate acid. So now we are looking this way. Accept proton, conjugate base. got H plus more, conjugate base. Donate H plus, conjugate acid. Donate H plus, conjugate acid. Accept H plus, conjugate base. Okay? Okay. And we are done with chapter 8, equilibrium, part 3. Okay, thank you very much.